I would like to tell you about organic materials for terahertz technologies. Uh, Before my report, I would like to inform you that we plan our joint project, the Center of Excellence of Ukraine for Future Terahertz Plasmonic Technology. This project is in the preparation stage now. The main idea of the project is to create the B-Center European Hub in Latvia and Ukraine to research, develop, and distribute innovative terahertz technology in all areas of human activity. The project consortium led by FOTONIKA-LV at University of Latvia and formed from research teams in Ukraine, Germany, France, Greece, and Lithuania. In our Institute of Semiconductor Physics, we have enough world-level group of theoreticians who deal with development of terahertz technologies. We have experimentator who deal with infrared and terahertz region of detectors, and many people deal with plasmonics. So this is very good base for our project. The main mission of the center is to ensure intellectual mobilization of human capital of Ukraine in the field based on partnership across Europe, European research area, aiming to take leadership in the field granting competitiveness of European Union in worldwide market. It is expected that performed research in the center will result in many game-changing proof and relevant activities in the from 3 to 6 years. And we hope that war between Ukraine and Russia will be finished, and we can send our project for after war rebuilding of Ukraine in general and Ukrainian science as well. What is terahertz? A terahertz is a range between microwave and infrared electromagnetic waves. We can see such position in scheme of electromagnetic wave. As usually, terahertz divided or 5 bands: sub-millimeter range from 0.1 to 0.3 terahertz, the low range from 0.3 to 1 terahertz, the mid-range from 1 to 3 terahertz, the high range from 3 to 10 terahertz, and ultra-fast range about terahertz. This area of research and application is very big. We present our vision of our future activity in the project in such diagram. We can see theory and modeling, application, and technologies and devices. And each of this direction can be enough big with many sub areas. And I would like to tell only 2 devices and a little materials, because technologies is a very big area, it's necessary to make a separate report, as well as for application is very big area too. Terahertz devices, this is not all, but main devices: quantum cascade lasers, photoconductive antennas, terahertz time domain spectroscopy, optical rectification, plasma-based generators, terahertz detectors, bolometers, photoconductive detectors, Schottky diodes, pyroelectric detectors, graphene-based detectors, etc. For terahertz, there are many conventional materials. First of all, this is semiconductors: gallium arsenide, gallium nitride, indium phosphide, cadmium hydrogen tellure, which are used to generate and detect terahertz radiation. Optical materials: gallium selenide, thin cadmium telluride, barium boride, etc., which are used to filter and modulate terahertz waves. Plasmonic materials: metals, gold and silver, sometimes used to focus and amplify terahertz signal, etc. You can see such references which I used when I prepared my report. And there are some new materials, for example, graphene, last decade it used and investigated very hardly. Metamaterials, superconductors, nanostructures, organic materials, etc. Why organic materials? This is one of big area of materials for electronics. Maybe last 30 years, a very big development has for many areas of electronics. And there is even Organic Electronics Association, which deal mainly with printed electronics and flexible electronics, and advantages of organic materials: flexibility and lightweight, low cost, scalability, tunable properties. But organic materials have enough big challenges: lower efficiency, material stability, and charge carrier mobility. It's necessary to have, for example, charge mobility of the best organic materials, about 1 watt centimeter second in the second. It's necessary to have maybe 10,000 or more times quicker material. I would like to present some examples of organic materials for terahertz generation. First of all, this non-linear and non-linear optical crystal. The most famous materials I present here: OH1, 2, 3, 4 hydro X-real, 5, 5 dimethyl cyclohexane, 2 aniliden, malonitrile, nitrile. As the first material, and the second HMQ TMS, 2, 4 hydroxyl, 3 methoxysterol, 1 methyl quinolinium, and 2, 4, 6 trimethyl benzene sulfonate. This material used last decade for generation of terahertz waves. Here I show crystallinity of this material, and here red arrows indicate direction of main charge transfer axis of the non-linear optic chromoforms. We can see that generation of second, third harmonics of electromagnetic waves in the range. Sorry, I didn't tell this is about 0.1 terahertz, and here 10 terahertz. So we can see in a middle range some peaks of electromagnetic waves, and this is very effective and promising materials for generation. Some materials in addition, OH6 FQ, fluorinated cationic shock chromophore, and NMBA, nitromethylbenzylidene aniline. This is usually used materials too for generation of electromagnetic waves. Some materials for detection of terahertz waves. The same materials that for generation, and it can be used also for detection of terahertz waves. This is a huge number of different materials, and I would like to tell that our institute have some experience in carbazole materials and heterocyclic amines, and I show some examples of such material we plan to investigate and use for terahertz technology. The carbazole materials, for example, 2 carbazole PN, 4 carbazole TPN, and 4 carbazole indium PN were investigated by 0.5, 4.5 terahertz spectroscopy. The absorbance lines were recognized and attributed to some wagging, rocking, rotational, and out of plane bending motion of the carbazole moieties. I would like, you can show some materials. I think that for scientists who didn't deal with organic electronics, it's not clear, but you can see that huge number of material which can be used for terahertz technologies. In conclusion, I would like to say that organic materials highlight the great potential for a wide range of terahertz applications. Organic materials need further research to improve their functional efficiency and lifetimes. Heterocyclic amines and carbazole derivatives are good candidates for various terahertz devices. Thank you for your attention.